Section 4.2, the mean value theorem. We first start with Rolle's theorem, where if f is a function that satisfies these three hypotheses, 1, f is continuous on the closed interval from a to b, f is differentiable on the open interval a to b, and f of a equals f of b, then there is a number c in this interval such that the derivative at c is 0. So we're saying that, let's say here's some function. It goes, oops, no, can't backtrack. Has some function, goes crazy. Okay, so over here is, let's say, a, and over here is, let's say, b. So then f of a is equal to f of b. They have the same y value. It's got no, points where it's going to be not differentiable, so no sharp points, no discontinuities in the closed interval. And Rolle's theorem guarantees that there's a number in here somewhere where the derivative is 0. Okay, so to prove this, we break it down into a number of cases. First, if the function happens to be a constant, so if it happens to equal k for some constant, then the derivative is 0 at every single point in there because derivative of a constant is 0. Okay, so next case, suppose that f is bigger than f of a for some f of x in the interval. So going back to our picture, instead of going down, assume that it might go down, but then it goes up a little bit at some point. So at some point in the interval, that f of x is bigger than the ny value. Okay, so in that case, it must have a local maximum somewhere. It could be over here, or it could be somewhere else. But it has a local maximum somewhere by the extreme value theorem. We know that local maximum is inside of the open interval, not the closed one, because f of x is bigger than f of a. So it can't be on the endpoint. We also know it can't be on the other endpoint because f of b is equal to f of a. Okay, since f is differentiable on the open interval ab, f prime of c is 0 by Fermat's theorem. So you could do the exact same thing, supposing the next case where instead of f of x being bigger than f of a, you suppose that f of x is smaller than f of a. And you'll see that by the same reasoning, you'll get some number c such that f prime of c equals 0. So let's do an example. How could Rolle's theorem be applied to a position function that models a ball thrown upward? Well, let's say that our position function is s equals f of t. Okay, and let's suppose that if t equals a and t equals b, then f of a is equal to f of b. In other words, the ny values are equal along some interval from a to b. Okay, so then Rolle's theorem comes in. So Rolle's theorem implies that there exists, I use this backwards e for there exists, some value c inside of our interval from a to b, such that its derivative is 0. Or the derivative is 0 at c. So that means that, well, that's derivative of position. So that means that the velocity is 0. Okay, so this tells you that if you take a ball and you throw it upward, then at some point the velocity will go down to 0, which should make sense because at some point the ball, when you throw it up, is going to end up coming all the way back down. Okay, let's prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. Remember, we've used the intermediate value theorem previously to prove that equations have roots We have not done it with this exactly business, but that's where Rolle's theorem will come in. We'll use the intermediate value theorem to prove that the root exists, and then we'll use Rolle's to prove that there can't be any other roots. So let's start with letting f be equal to this polynomial, x cubed plus x minus 1. We're looking, let's see, we want to show that it has one real root, so we want to show one y value of 0. So let's choose some x values that give y values a little bit below 0 and a little bit above 0. Notice by inspection, if I plug in 0 for the x's, then I get minus 1. So that's a little bit below 0. So f of 0 is minus 1, below 0. And if I plug in 1, it's another easy number to plug in, then I get 2 minus 1 equals 1. So f of 1 is 1, which is above 0. Okay, this is a polynomial, so it's definitely continuous on the closed interval. We also have some y value a little bit below the y value we're looking at, 0, and a y value a little bit above the y value we're looking at. So the intermediate value theorem, IVT, tells us that there exists a c inside in the interval from 0 to 1 such that f of c is equal to 0. Okay, so we've proven that a root exists. The next step is now to show that there can't be any others. So let's suppose, towards a contradiction, that a and b are roots. We're going to show that this is impossible, that only one of these guys can actually be a root. Okay, well, if there are two roots, then we know that each of those, remember by definition, a root is an x value that gives a y value of 0. So f of a is 0, and f of b is also 0 because they're both roots. Okay, so that means that we can use Rolle's theorem because we have a continuous function. The polynomial is continuous in the closed interval. It's differentiable in the open interval. And we have f of a equals f of b. So Rolle's implies that there exists a c inside the interval from a to b such that the derivative at c is 0. Okay, but there's one problem with that. If you take the derivative of this guy, we get that it equals 3x squared plus 1 by the power rule. Well, x squared is strictly greater than or equal to 0. So the least this thing could possibly be is 1. So this thing is greater than or equal to 1. And that's for all, I'm using the upside down a, for all x values. So for any x value you plug in, this thing's going to be greater than or equal to 1. So it's impossible that it equals 0. So that's a contradiction. So it must be that we weren't allowed to invoke Rolle's theorem in the first place. In other words, there could not have been two roots. So f cannot have two real roots. Notice by the fundamental theorem of algebra, it has 3 roots, but so it has 2 complex roots. However, we're not going to get into that. It's not really part of this calculus course, but just want to stress that this real condition matters. It actually does have the other roots. Okay, the moment we've all been waiting for, the mean value theorem. Suppose f is a function that satisfies these hypotheses. It's continuous in the closed interval and differentiable in the open. So we only need the first two for Rolle's theorem. Okay, well then there's a number c in the interval such that the derivative is equal to this guy. However, that looks very familiar. That is the slope of the secant line, or the average rate of change, whereas the derivative is the instantaneous rate of change, or the slope of the tangent line. So this tells you that somewhere inside of our interval, if the function is continuous in the closed interval and differentiable in the open, then the derivative will be equal to the average rate of change. The slope of the tangent line will be equal to the slope of the secant line at some point. So that's pretty cool. You can multiply both sides by b minus a, and if you want to get everything on one side like this, and then you can get f of b minus f of a is that. That's the same thing. Okay, let's see if we could prove this. What we're going to do is we're going to concoct some function h, where h is the difference between f and the secant line to f on the interval, the closed interval ab. So here's f, and here's the secant line to f. Notice that to build the equation of a line, we can use point slope form. So y, let's say minus y1 equals m times x minus x1. However, m is this guy. That's the slope of the secant line. So that's where this comes in. And then if I wanted to, I could just move over the y value. So this is the same thing as y1 plus m times x minus x1. So that's where this f of a is. That's my y value at a. And this is the x value at a, which is just a. So that's where this comes in. Let's go back. Okay, so then h is continuous on AB. Why is it continuous on AB? Because we're assuming that f is. And this function is obviously continuous on AB. This is, oh, I even wrote, it's a sum of f in a first degree polynomial. Okay, so that means it's also differentiable on the open interval. So what we can do now is a little bit of a trick. We take the value of HA. So if we plug in A for all of the x's, then notice what happens. You end up with f of a minus f of a cancels. So let's pull out another color. So this is gone. And then a minus a cancels and leaves you with 0. So that actually kills off this whole thing because 0 times this thing is 0. So you end up with 0 if you look at what h of a is. If we look at what h of b is, then we have b minus a cancels and gives you 1. So then you have f of b minus f of b is 0. And we have minus f of a minus a minus is plus f of a is 0. So h of b is also 0. Okay, so that's pretty cool because remember, if we have these two conditions and we have this third condition where h of a equals h of b, then we can use Rolle's theorem. So by Rolle's theorem, there must be a number c in this interval such that the derivative at c for h is 0. Okay, so we know that 0 is h prime of c. But we know that h prime of c is actually equal to this thing. Why? Well, go back to how we defined h. Notice that if we take the derivative of h, we get f prime of x. F of a, well, that's a constant, so derivative is 0. Same thing over here with this a, 0. So that means I have a constant times x. So when you have a constant times the variable x, remember the derivative is just that constant. You lose the x. So that's why you end up with this. You get f prime of x minus f of b minus f of a over b minus a. And then you plug in c for the x value, and it becomes this. Okay, so that's pretty cool because I have 0 equaling this. So I can just add this thing to both sides. I get f prime of c equals this. Well, that's exactly what we wanted to prove. We wanted to prove the derivative at c is equal to the average rate of change. Let's find a number c in the interval 0, 2, such that the slope of the secant line is equal to the slope of the tangent line for the function f of x equals x cubed minus x. Notice x cubed minus x is a polynomial. It's definitely continuous on the closed interval 0, 2, and is definitely differentiable on the open interval 0, 2. So by the mean value theorem, this value of c definitely exists. Right? There exists a c inside the interval from 0 to 2. such that f of 2 minus f of 0 is equal to f prime of c times 2 minus 0. That's our mean value theorem when you multiply both sides by mu minus a. Okay, so what's f of 2? Well, that's 6 if you plug in 2. And then f of 0 is 0. So 6 minus 0 is equal to 3 times c squared minus 1, because the derivative of x cubed minus x is 3x squared minus 1, so we just plug in c. And then times 2 minus 0, which is times 2. Okay, we can simplify this, so we have 6 equals 6c squared minus 2 by distributing. And then we solve for c, and we get, well, first we solve for c squared, we get c squared is 4/3. So that means that c is equal to plus or minus the square root of that, so 2 over rad 3. However, if we look at minus 2 over rad 3, we know that that's not in 0, 2. So we can reject that. We can see that c has to be positive. So c must be equal to 2 over rad 3 in order to be in the interval 0 to 2. Okay, pretty cool. If you look at a graph, we can illustrate the mean value theorem. So this function looks something like, maybe something like that. And let's say here's 0. And we want to go all the way up to 2. So I'm going to cheat a little bit, draw the secant line first, and then go right underneath and say that that's 2. Okay. So there's x, there's y, and this is the graph of x cubed minus x. The line I just drew is the secant line that cuts through x equals 0 and x equals 2 at the y values 0 and 6. This mean value theorem that we just did says that there is a guaranteed value for c, which is at 2 over rad 3, roughly over there. So that's x value c, such that if I were to draw the tangent line to the curve over there, then the slopes match. You can't tell it from my terrible drawing, but this line, that's the secant line, and this line, that's the tangent line, actually do have the same slope. So their slopes are equal. That means the derivative is equal to the average rate of change over the entire interval from 0 to 2. Pretty cool. What does the mean value theorem say about the velocity of an object moving in a straight line? Well, the velocity, or the average velocity, is the slope of the secant line. Mean value theorem says that that must be equal to the derivative, which would be the instantaneous velocity. So it says at some point, or how about at some time, the average velocity is equal to the instantaneous velocity. You could see this as an example if, let's say a car was traveling, let's say it went 180 kilometers in 2 hours. So it traveled 180 kilometers, it traveled it in 2 hours. Well, then the average rate of change is 90 kilometers per hour. So by the mean value theorem, that speedometer on the car must have actually read exactly 90 kilometers per hour at least once during that journey. It must have actually read that average rate of change. Okay, suppose that f of 0 is -3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? Let's use the mean value theorem. So we've got f of 2 minus f of 0 equals f prime of c times 2 minus 0 for some c. we're going to try to use the mean value theorem to get some kind of information on f of 2 without even knowing what the function is. Alright, let's solve for f of 2. So that's f of 0 plus 2 minus 0 is 2, so 2 times f prime of c. And that equals negative 3 plus 2 times f prime of c. Because they told us f of 0 is negative 3. So we only have one other piece of information here. F prime of x is less than or equal to 5. So let's use that now. Well, if f prime of x is less than or equal to 5, that means that f prime of c is less than or equal to 5. Because that was true for all values of x, c is a value of x. Okay, so we needed an estimate on 2 times f prime of c. So that means that 2 times f prime of c is less than or equal to 2 times 5, which is 10. So going back to what we have for f of 2, we know f of 2 is equal to negative 3 plus 2 times f prime of c. And we know that that's less than or equal to negative 3 plus 10, because 2 times f prime of c is less than or equal to 10. So that's 7. So f of 2 must be less than or equal to 7. So the largest possible value for f of 2 is 7. Okay, time for another theorem. If the derivative at x is 0 for all x in an interval ab, then f is constant on ab. This is the converse to what we had before, where if you take the derivative of a constant and you get 0. So now we know that the reverse is true. It took us a while to get to this point, but it's kind of cool. Notice this is only true, though, if it's 0 for all x in an interval. If we look at some other functions, like let's say f of x is equal to x over absolute value of x, that, notice, is equal to 1 if x is positive, because then you get just x over x is 1. It's equal to minus 1 if x is negative. So if you take the derivative for x being positive, you get derivative of 1 is 0. Derivative of minus 1 if x is negative is also 0. So f prime of x is 0. But notice the domain is not an interval. In this case, the domain D is all of the x values such that x is not equal to 0. That's not an interval. That's 2 intervals. It's the interval from minus infinity to 0, not including 0, and it's the interval from 0 to infinity. Notice that f is constant over here. It's 1 over here, because then you can actually use this theorem. And f is constant over here. It's minus 1 over there. Oh, sorry, I reversed that. It's minus 1 over here and 1 over here. But it is definitely not constant over the entire thing, because the entire thing is not an interval. So you have to be slightly careful here. All right, let's prove this really quick. Let x1 and x2 be 2 x values inside of the interval ab. Okay, we want to make them so that one is smaller than the other one. That way we can make a new interval out of them. So we make this new interval from x1 to x2. Well, by the mean value theorem then, we know that the derivative is 0 for all x in interval ab. So we can apply the mean value theorem. It's differentiable for all x in there. Then it's definitely continuous on this closed interval and differentiable there. So we can use the mean value theorem. We get f of x2 minus f of x1 equals f prime of c times x2 minus x1 for some c in the open interval. But the derivative is 0 for all x in the interval. So that means that this is 0. It's gone. So this entire thing becomes 0. So that means that this thing equals 0. So if they equal 0, you can add this guy to both sides and get that they equal each other. So that means that any two y values will be equal to each other. because we chose x1 and x2 completely arbitrarily. So if any y values are equal to each other, then that means that all the y values are equal to each other. So f is constant on the entire interval. Let's do a quick corollary. If f prime of x equals g prime of x for all x in an interval ab, then f minus g is constant on ab. In other words, f of x is equal to g of x plus some constant. So they're the same function, one is just moved up. Okay, let's prove that. So that's actually kind of cool. If two functions have the same derivative, then they must be basically almost equal to each other. Okay, so let's let big F be equal to this difference function. Well, then the derivative is the difference of the derivatives, right? But we know that the two derivatives are equal to each other. So this is the same as f minus f, which is 0, or f prime minus f prime, which is 0. Well, the derivative is 0, and it's 0 for all of the x in an interval. So that means that it's constant by the theorem we just proved. So if this guy is constant, that means f minus g is constant, because that's just the way we defined it. Okay, let's prove the identity tan inverse x plus cotangent inverse x equals pi over 2. You could prove this directly using some manipulation, and it's just a standard trig proof. However, there is a cool calculus proof. Let's do that. Let's let f of x be equal to this function, tan inverse plus cotan inverse. Okay, so then the derivative we know is 1 over 1 plus x squared for tangent, and minus 1 over 1 plus x squared for cotangent. So that's 0. So the derivative is 0. That implies that f is constant. So f is some constant, let's say big C. So that means that that constant is equal to f for any x value we plug in. So let's choose an easy x value to plug in over here to evaluate it, because we know tan inverse x is constant, so it doesn't matter what x value we plug in. Well, an easy value for tan inverse is 1, because we know that at 1, sine is equal to cosine, so that's at pi over 4. So let's plug in 1 for x, because that's easy for us to evaluate. So f of 1 is tan inverse of 1 plus cotangent inverse of 1. So they both have the same, because that's when sine and cosine are equal, so it doesn't matter the order you divide. So that's pi over 4 plus pi over 4, which is pi over 2. Okay, so then that means that it must be that tan inverse of x in general plus cotangent of inverse in x in general must be equal to pi over 2, because we just proved that they're constant. So if they equal pi over 2 for a single x value, they equal pi over 2 for every x value.